Let's pick up where we left off with number 13 in the review. Let's see, I'm going to have to minimize. There we go. So I can see my screen. What's the standard cell potential for the spontaneous reaction between these two half cells? We're told two important facts here. This reaction is spontaneous. That means we need a voltage that is positive. We're also told that it's a standard cell potential, which means it doesn't matter what the concentrations are. The standard is, by definition, 1 molar. So all we have to do is decide and let's see, silver. And the reduction potentials, the standard reduction potentials are given as 66 volts and plus 080 volts. All we have to decide is which one's the anode, which one's the cathode. And we do that by saying we can't have both reductions. One of them has to be an oxidation. So if we make silver an oxidation, flip it, that changes this to a negative. And when you add those two together, you get a negative. So we can't be that one. We have to change this one. We have to do that. That changes that positive. Then we can add them together. 2.46 volts is the standard cell potential for this combination. Right? Number 14. The oxidation number of manganese changes from what to what in this redox reaction? All right. Where is manganese? On the reactant side, we have MnO4 minus. Right. And on the product side, we've got MnO2. Okay. So to answer the question, all we need to do is find out what's the oxidation state for manganese in these two, right? Oxygen by definition is -2. So -2 times 4 is -8. We're going to hold one of them out for that minus. That means that one is +7. Again, -4. This is a neutral compound, so we have to neutralize all of those minuses. So we're going from +7 to +4. All right, 15. What's the equilibrium constant expression for this reaction? All right, two things. The equilibrium constant, of course, is the product of products in the numerator and the product of reactants in the denominator with their respective powers derived from the coefficients. But we also have to eliminate solids and pure liquids. So that means C6H12O6, which is probably glucose, is a solid. We don't include it because its concentration will not change. Concentration of water, it's a pure liquid, leave that one out also. So we have CO2 in the numerator. To the 6th power. And O2 in the denominator to the 6th power. Okay. That's the equilibrium expression for that equation. All right, 16. For an endothermic reaction performed at two different temperatures, which condition gives the highest concentration of products at equilibrium? Assume that temperature is the only variable. Okay. For an endothermic reaction. So we have reactants yields products, and this is an equilibrium situation. And this is endothermic. So the heat goes in as a reactant. And we're performing the procedure at two different temperatures. Which condition gives the higher concentration of products at equilibrium? Okay. So at one temperature, we get a certain amount of product. At the next temperature, if the temperature is higher, we'll increase this one and drive the reaction that way. So low temperature is, say, well, that's not a good choice. Let's do product 1. And high temperature would be product 2. Since it's endothermic, product 2 is going to be greater than product 1. So the reaction at the higher temperature will produce the higher concentration of products. This is purely Le Chatelier. Now we know that the equilibrium constant is actually changed when we change the temperature. But for the use of, to use Le Chatelier's principle, we don't have to consider that. All we need to know is where is this term? Is it on that side or that side? Right, 16, 17. Which equilibrium shifts to the left upon an increase in volume? Okay, if we're going to change the volume, what type of reaction responds for change in volume? I heard a ding-a-ling. Let me see who it is. Ah, Michaela. Okay. All right. So for the effect of volume is only felt by reactions that have gases and for reactions that have different moles of gas on the product side versus the reactant side. So if we're looking for a change, if we're going from reactant gas to product gas, and we're looking for the equilibrium that'll shift to the left for an increase in volume. If we increase the volume, what's the system going to do? It's going to try to make more moles of gas if there is a difference between the two. So if we want more moles of gas, we need an equation that has coefficients for the gases totaling a larger number on this side than on that side. And let's see. I was just checking out the others. We know the answer is A, but I was looking at the others just to see if there was any. C is equal numbers of moles, so that won't be it, definitely. D is 9 moles of gas on the reactant side and 10 moles on the product side. So an increase in volume for that one would drive it toward the products. Right? A, where we have 3 moles of gas on the reactant side and 2 moles of gas on the product side. If we increase the volume, the system is going to try to fill that extra space with gas molecules, and that will shift to the left. All right, number 18. According to the collision theory for chemical reactions, why do most reaction rates increase as temperature is increased? So at higher temperatures, complete the sentence, A, B, C, D, C, or D. Why? All right, for the collision theory, what do we need? Right? We need a collision. Reactions must contact one another. We also need an activation energy, a certain amount of energy. And we need orientation. So which factor are we talking about here? We're talking about increase in temperature. That's this factor right here, activation energy. And remember, for our reaction energy diagram, right, this is progress of the reaction, that direction. And this is energy. So if we want to speed up the reaction, what part of this are we talking about? If these are reactants and these are products, this is here, activation energy, right? So what part of this diagram are we talking about with rates? This part over here and here is equilibrium. This part in here is kinetics. That's rate. So if we increase the temperature, we're going to have more molecules exceeding the activation energy and the reaction rate will increase. So C is the answer. At higher temperatures, more molecules collide with the necessary energy. All right. Let's see, 19. Okay. Let me see, consider this reaction mechanism. Step 1, step 2. So the first step is a slow reaction rate. Second step is a fast reaction rate, and the overall reaction is below. And we can assume that the rules are met. If we add step 1 to step 2, we get the overall reaction. The overall reaction is blank order with respect to NO2 and blank order with respect to Cl2. Okay, where do we get the order of reaction when we're looking at the mechanism? We're looking at the bottleneck, the slowest step. So we focus on step 1, right? And with mechanisms, overall reactions, right, for the rate equation, we have to do it experimentally. But if we're proposing steps in a mechanism, the mechanism itself will tell us what the order is. So the overall reaction is based upon the slow rate, the slow step. So the coefficient for NO2 is 1, and the coefficient for Cl2 is 1. So their orders are first and first, both of them, based upon the mechanism. Now, if that mechanism is wrong, then, you got to look at a different step. But based on what we're given, they're both first order, because that's the slow step. That's the rate determining step. Number 20. What is the intermediate in this reaction mechanism? Right? When you're looking at mechanisms, if you're looking at overall reactions, you can pick out the why does this happen to me? Maybe I'll take a drink and see if that helps. Oh, yeah, that helped. With the overall reaction, you can pick out the catalyst because it goes in one side, comes out the other unchanged. But in order to find the intermediate, you need mechanisms, because the intermediate appears within a step and disappears before the reaction is complete. So if we look at these two steps, which one of those appears and disappears based upon the net reaction? O3 and O yields O2. Right? In the first step, the chlorine, which is probably a radical, free radical, it enters and comes out. So that's a catalyst. The intermediate appears on the product side of the first step, ClO, and disappears before the reaction is complete. So the intermediate is ClO. All right. 21. Which statement best explains why a catalyst increases the rate of reaction? All right, let's go back to our energy diagram. How do we depict the effect of the catalyst on this energy diagram? We have a lower activation energy. So how do you get a lower activation energy? You can't go through the same steps of mechanism in order to get there. Right? It'll just take you to the same place by the same route. It won't change the speed of the reaction or the rate of the reaction. You need a different mechanism to give you the effect of the catalyst. So the explanation for the increase in the rate of reaction based upon a catalyst is it provides an alternative mechanism with a lower activation energy. All right. And let's see, we can get all of 22 on there. 100 milliliters of liquid ethanol at the same temperature are placed in each of the closed vessels shown below. Right? So we have a difference in size. After equilibrium is established, which vessel has the smallest mass of ethanol vapor? If you consider what's happening in the vessel of any of these sizes, you have a certain volume here, and you have evaporation, and eventually you get enough molecules up here that they start returning. Once you reach equilibrium, and it's based upon concentration, right? So if you have a larger space, that means you need more gas molecules in that space to give you the same concentration that's required for the vapor pressure. So if you want to build up vapor pressure more quickly and with fewer gas molecules, you need a smaller vessel. So vessel 1 is the small vessel. It has a smaller head space. Fewer gas molecules are required. So it puts less of its mass into the vapor phase. Right? So at equilibrium, the smallest mass of ethanol vapor will be in the smallest vessel, vessel 1. Okay. The largest mass, by contrast, will be in the vessel 3 because it has more headspace that must be filled in order to reach the vapor pressure. Vapor pressure is an intensive property, and it has to be reached by whatever means. '23. All right, the enthalpy of vaporization for a substance is significantly larger than the enthalpy of fusion because the enthalpy of vaporization, right, is significantly larger than the enthalpy of fusion. Now, the enthalpy of vaporization, we can That's self-explanatory. It's just how much heat does it take to go from a liquid to a gas? The enthalpy of fusion is a little more cryptic. Enthalpy of fusion is how much energy does it take to melt the solid into the liquid phase. Okay. So why is this one so much bigger than that one? Well, think about what happens. If you go from a solid to a liquid, what do you have to do? You have to break some intermolecular forces that are holding the solid together in its regular structure, just enough so that those molecules now can pass by one another. That goes from here to here. When you go from a liquid to a gas, which is this heat, you need enough energy to actually break any intermolecular forces that are holding the molecules together. Not just to let them slide past one another. They have to be independent players, independent molecules, far apart with lots of energy. Lots of energy means lots of heat required. So to form a vapor, all intermolecular forces must be overcome. That's why the gas laws work just as well for air or for helium or for any other gas. Doesn't matter, because they act independently. There are theoretically, no forces holding them together. Now, we know they do interact some, but at those energies, the intermolecular forces between gas molecules are insignificant. All right. How about 24? Which aqueous solution has the lowest normal boiling point? All right. I think we need Henry Ford for this one. The lowest boiling point. So let's say A, B, C, and D. And D is, they all have the same boiling point. Okay. So the first one is 0.1 molal, 0.1 molal, C2H5OH. That's ethanol, the drinking kind. 0.1 molal, sodium chloride. And I assume that this is an aqueous solution, right? It would have to be to make sense. And then 0.1 molal potassium phosphate, right? These are all soluble, right? So when we put them in solution, what do? Well, this one is still ethanol, just 1-to-1. So that means it's 0.1 molal. How about sodium chloride? Well, it produces sodium ions and chloride ions. So it's 0.2 molal in ions. And potassium phosphate produces 3 potassiums, 1 phosphate, and 1 phosphate. So that's 0.4 molal in ions. Now, how do we answer the question? The lowest normal boiling point. Remember the expression, a change in temperature for boiling point is equal to the Van Hoff correction factor, the boiling point, elevation constant times the molality, right? So these two right here, we can combine in those values right there. Or we could say 0.1, and then the correction factor would be 1, 2, and 4. Either way works. All right, that's a constant. So we want to increase the boiling point. So we need more moles, a higher concentration of ions or product, molecules or ions. Right? So the one that has the greatest number of ions produced in solution, let's see. Oh, I'm sorry. I was looking for I read the question, right? Lowest normal boiling point. So the highest normal boiling point would be this one, right? The lowest normal boiling point would be that one, because its correction factor is 1. All right. And this factor right here, this is for the solvent. Those are solutes. This is the solvent. So it's going to be the same value, assuming it's aqueous solution, it'll be whatever it is for water. So this has the lowest normal boiling point. This has the highest normal boiling point. They're not all the same. All right, 25. A sample of water from the Great Lakes was taken in 2022. Blue smoke. The sodium chloride concentration was 10.2% mass. Right, sodium chloride concentration. Is 10.2% mass. Okay, what does that mean? That means 10.2 grams of sodium chloride for every 100 grams of solution. The molar mass of sodium chloride is 58.44. Okay. The density of the solution is 1.195 grams per milliliter. Okay. What's the molar concentration of sodium chloride in this sample of seawater? This is a dimensional analysis problem. We're going to go from this value to what? Moles of sodium chloride per liter of solution. The molar concentration per liter of solution. Okay, so how do we get there? Well, remember when you've got a starting point that has more than one dimension involved. We've got mass on top and mass on the bottom. Do one at a time. So I'm going to do the mass on the bottom first, the mass of the solution. Right. So this is, excuse me, grams of solution to milliliters of solution. Okay. So grams of solution to milliliters of solution. 1.195, except that's per 100 milliliters, right? So this 10.2% is so many grams per, oops. Let's make it easy on ourselves. Let's change this factor. If this is grams per milliliter, this would be 100 grams per gram. Right? 10.2 grams per 100 grams. There you go. Okay. And this is 1.195 grams per milliliter. There we go. Okay, now our multiplier here is going to be 100 and here's going to be 1. But this is grams of solution here. Okay, so we got rid of grams of solution, but we still got the 100 factor. We have to keep that in mind. And this gets rid of grams of solution here. Okay, so we got milliliters of solution. Now we need liters of solution. So we have 1,000 milliliters per liter. There we go. And now we got liters of solution taken care of. Now we need moles of sodium chloride. We got 10.2 grams of sodium chloride, and we want to change it to moles. Right? So we got 58.44 per mole. That gets rid of grams of sodium chloride, leaves us with moles. So now we just need to crunch some numbers. All right, I'm going to change this display. There we go. Okay, so we have 10.2 grams per 100 grams. 10.2 divided by 100 times 1.195 here times 1,000 divided by 58.44. So I get, let's see, 3 significant figures, 2.09 molar. Okay. 25. Twenty-six. What is the sign of delta S for this reaction? So we have O2 and 2H2. O2 plus 2H2 yields 2H2O. H2O. Gas. All right. we got to simplify this as much as possible because we're not given any values to calculate with. We have to assume that we're working with a situation of disorder. So which is more disordered? There's 1 mole here, there's 3 moles gas on this side, and only 2 moles on this side. So if it goes from this to that, delta S is decreasing. Right? It's decreasing. Now we know this is a spontaneous reaction. All you have to do is get it started. Oxygen and hydrogen, yeah, we shoot rockets into space with this stuff. So we know that the reaction is spontaneous, only the delta S is less than 0. So that means if we look at delta G equals delta H minus T delta S, and if this is negative, that makes this whole thing positive. That means this one has to be exothermic enough to overcome that one. This one has to be big to make this one negative because delta G negative is spontaneous. That was extra. That was free. You didn't have to pay for that one. All right, 26, 27. Let me see. All right. I'm probably going to run out of time. 27. The pH of an aqueous 0.00796 molar solution of hydriodic acid is 2.12. What is the Ka of HiO3? Don't assume that ionization is negligible. Do not assume that ionization is negligible with respect to the initial concentration. Okay, so what do we know? We know the concentration of HiO3. So in aqueous solution, it's going to produce that and that, right? Aqueous solution. And we also know that the concentration of HiO3 is 0.00796, 0.0076 molar. And we know the pH is 2.12 pH. Okay. So if this is the initial concentration, right, what is this concentration at equilibrium? That tells us right there. And I can do better than that. H. There you go. So what's the hydrogen ion concentration? It's 10 to the minus 2.12, right? The anti-log of the negative 2.12. So let's see, what is that value? 2.12, change the sign, and then do 10 to the x. Okay, this is 7.59 times 10 to the minus 3. Okay, if we put this into solution, and it is derived from this one, that means this concentration must also be like that. Okay. Okay. So we know that. That means starting off with 0 here, and this is plus x. So this is 7 plus x. Actually, that's not right. It's 7.59 times 10 to the minus 3. We know what it is. But what's this one? This one has to be minus 7.59 times 10 to the minus 3. So this is 7.96 times 10 to the minus 1, 2, 3. Minus 7.59 times 10 to the minus 3. Okay, so let's figure out what is that value. Then we can calculate Ka. Right, 1, 2, 3, that's correct. And that's correct. Okay, 7.96 exponent 3 minus, and then flip those and subtract. So this is 3.74 times 10 to the minus 4. So now we can calculate Ka. Right? Ka is going to be hydrogen ions, iodate ions, and HiO3. Okay. So this one is 7.59 times 10 to the minus 3, but it's the same for both of them, right? So that's squared. And then in the denominator is 3.74 times 10 to the minus 4. All right, so let's see, 7.59 exponent minus 3, enter and square it. And then divide it by, let's see, I need to bring that down and flip them to get them in the right order. No, I better put them in myself. I can go back and start over again. And then square. Okay, so this one is 5.76 times 10 to the minus 5. Okay, divided by 3.74, 10 to the minus 4. There we go. Let's see. In standard notation. So this is 0.15403. Or rounded off 0.15. 0. All right. We've got some rounding error here. 0.16. Since there are none of the above, pick the best one. And the best one would be 0.16. All right. 27, 28. What's the pH of an aqueous solution of equal volumes of 0.6 molar nitrous acid and nitrous acid, HNO2, and 0.3 molar sodium nitrite? The Ka of HNO2s. All right. The easiest way to solve this one is Henderson-Hasselbalch. Log, that better. Log. And the conjugate base is going to be the nitrite ion. And the acid is HNO2. There you go. So now we need, let's see, we need pKa. We got 4.46 times 10 to the minus 4 is the Ka. Negative log of the Ka. 446 times 10 to the minus 4. Yep. So we need the negative log of this one to give us the pKa. And let's see, log, it changes sign. So this is 3.35. So that's 3.35. And then the log of this expression, NO2. What's the NO2 concentration? NO2 is delivered as sodium nitrite, 0.3 molar. And then HNO2 or nitrous acid is 0.6. Go. So what is that? That looks like a half, right? That's the log of 0.5, right? 3 divided by 6 is a half. So you've got this number. Now I want the log of 0.5. And then I'm going to add, which is a negative 3.0, actually, negative 0.301. So I add that to this one. And I get 3.05 pH. Okay. Number 29. Which is the most prevalent species in a 0.25 molar aqueous solution of phosphoric acid? And you're given the ionization constants for each one. The most prevalent species of 0.25 molar H3PO4. Remember, when an acid dissociates, a polyprotic acid dissociates, it dissociates one proton at a time. And the equilibrium constant for the second dissociation is much smaller than the first. And the third one is even smaller than that. So the dominant species in a polyprotic acid dissociation are the ones, in this case, H3PO4 is one proton here, and H2PO4 minus. So the dominant species, and this Ka for this one is 7.5 times 10 to the minus 3 times 10 to the minus 3. which means what? It means that there's not very much of this in there. Like it's 3 orders of magnitude, 2.5. So the dominant species is still that one right there. Okay. All right. Moving on. To 30. Which species is the most powerful oxidizing agent at standard conditions? An oxidizing agent. Oxidizing agent. Most powerful oxidizing agent is the most easily reduced. So the one that's most easily reduced is the more positive of the reduction potentials. Right? So which one, all of these values here are given as reduction potentials. We want the most positive one. That will be the one that's the strongest oxidizing agent. And the last one, 0.54, is the largest positive number. Iodine, I2 solid, is answers the question. All right, I2. Most easily reduced as the most positive reduction potential. All right, 31. A current of 0.15 amps is passed through an aqueous solution of copper sulfate for 20 minutes. What mass of copper is plated out? Assume 100% yield and molar mass of copper is 63.55. Okay. So what reaction is going on here? Right? If we're plating out copper, then we've got, if copper sulfate is in solution, right, in aqueous solution, what is it going to produce? It's going to produce, right, that's CuSO4? Yes. It's a 2+ ion and a sulfate ion. Right? That makes sense. Right? One of these. We know that sulfate is 2-. The sulfate ion is 2-. So copper has to be 2+. Now the reaction that we're interested in is 2+ aqueous plus some electrons yields copper metal. Okay, that's the one we want. So if we pass a current of 0.15 amps through this solution, we're providing it with those electrons. So 0.15 amps. What's an amp? It's a coulomb per second. Coulomb per second. Right? At this point, it becomes a dimensional analysis problem. So in order to relate this charge to that equation, we need to know how many moles of electrons are actually being delivered. So with this amperage, how long does it go on? 20 minutes? 20 minutes. Which is how many seconds? Times 60 seconds. Right? 1,200 seconds. Right? Yeah, 2 times 6 is 12, and 10 times 10 is 100. So 100 times 12 is 1,200. Okay, that gets rid of seconds. Now we need to convert coulombs to moles of electrons. Coulombs on the bottom, moles of electrons on the top. So we need Faraday's constant, which I don't have memorized, so I'm going to look it up. I think it's 96. 96,485. 96,485 coulombs per mole of electrons. Okay, that gets rid of coulombs, moles of electrons. Now, what's the ratio of moles of electrons to moles of copper? It's 2 to 1. Okay. Now we want to convert moles of copper to mass of copper. Okay. 63.55. There we go. Now all we have to do is crunch some numbers. So 0.15 times 1200 divided by 96,485 divided by 2 and times 63.55. So I get, let's see, standard notation. All right, so let's see, I got to move my decimal place 0.059, 3 significant figures. 93 grams. Okay. Right, 31 and 32. Good. 20 minutes. The reaction A equals products obeys the second order kinetics. So if A equals products and it's second order, okay, that's given. What is the molar concentration of A remaining after 3 minutes? If the reaction has a rate constant of 0.0482 and the initial concentration of 0.379. Okay, if this is second order kinetics, what rate law is applied? Remember, if we graph, right, and we say concentration of, let's see, concentration of A, and this is time. If it obeys second order kinetics, this is inverse. Gives us a straight line. But what we want is the equation, not the differential, the integrated. We want the integrated rate law. The integrated rate law then would be 1 over A equals positive K times 1 over A 0 plus well, that's why I put it in here for you, so I get it right. Oh, KT, excuse me. That was dumb. KT, and then 1 over A 0, y-intercept. Okay, what are we given? Well, we're given time, 3 minutes. 3 minutes. We're given the rate constant, 0.0482. 0.0482, right? Yeah. But this is molarity seconds. So this needs to be seconds. 60 times 3 is 180, right? So this is 180 seconds, right? Initial concentration, 0.379. This is initial concentration, 0.379 molar. All right, I think we got everything we need. right? So the inverse of 0.379 is, so this factor here is 2.639. 180 times 0.0482 is 8.676. So add those two together, right? And this side of the equation is 11.314. But this is inverse, right? So we need to take the inverse of that value in order to be the actual concentration. There it is. Okay. 8.84 times 10 to the minus 2 molar. Oh, it's in standard notation. Okay. Two places to the left, 0.884 molar. There you go. Oh, that one's not even marked. How'd that happen? Yeah, that's supposed to be your answer right there. 0.0884 is the answer to 32. I missed one. All right. 33. All right, let's read what the question is, and then we'll have to scroll a little bit. Which energy diagram best illustrates a reaction that is thermodynamically disfavored and kinetically slow? Okay, when we're talking about progress, our energy diagram here, we want thermodynamically disfavored. That means it's endothermic. In other words, the products have more energy than the reactants. Right? Products, reactants. That's thermodynamically disfavored. Kinetically slow means a large activation energy. Like that. So which one looks like that one? A. So right there in front of you. A is the best choice there. So we took the conditions and drew the energy diagram, and then all we had to do was just find it in our choices. All right, 34. One version of Clausius-Clapeyron equation is natural log of vaporization pressure, vapor pressure, equals negative delta H for vaporization divided by RT plus natural log of beta. Okay, the slope of the straight line of blank can be used to determine the enthalpy of the vaporization. Oh, okay. So if we plot this on a graph and we make y the natural log of the vapor pressure, and we plot 1 over T temperature here, then that extracts this delta H over R times 1 over T. Right, there's your X, there's your Y. This is the slope of the line. It's going to be a negative value. Right? So we can use a plot of the natural log of vaporization against inverse of temperature. That's what that means. The slope of the straight line plot of that versus that will allow you to calculate the enthalpy of vaporization for this process. All right, 35. Silver chloride has a KSP, solubility product of 1.6 times 10 to the minus 10. Okay. What's the molar solubility of silver chloride in water? All right. So if the KSP is equal to 1.6 times 10 to the minus 10, correct? Now, what are we talking about? Solubility of silver chloride is in equilibrium with silver ions. This is going to be a solid. Solid. Plus chloride ions. Right? So what is this equal to? This is equal to silver times chloride. Like that. So what is that concentration? Well, if we drew our ice table and call this a change of solubility, right, then it's going to end up over here 1 to 1 to 1. This is plus S starting at 0, plus S plus S. Then we have S and S. Then this is simply going to be S times S, or S squared. S squared is equal to 1.6 times 10 to the minus 10. So S is equal to the square root of 1.6 times 10 to the minus 10. And that should be, for in the interest of time, should be 1.3 times 10 to the minus 5. Molar. That's the solubility, the molar solubility of silver chloride in water. 36. At 23 degrees, the vapor pressure of water is 21.1 millimeters of mercury. If 8.55 grams of sucrose is added to 7.6 grams of water, what's the vapor pressure of the solution? All right. Let's see. Well, let's see. What are we given? The temperature is 23 degrees. See. Okay. The vapor pressure of pure water, pressure of water at that temperature is 21.1 millimeters of mercury. Okay. 8.55 grams of sucrose. So the mass of sucrose is 8.55 grams. And its molar mass is 342 grams per mole. 342, right? Grams per mole. Okay. Added to 17.6 grams of water. So the mass of water is 17.6 grams. Okay. And it's 18 grams per mole. All right. So the question is, what's the vapor pressure of the solution? The vapor pressure, the actual vapor pressure of the solution is equal to the mole fraction of the solvent times the standard vapor pressure. of the solvent. Right? That's oh, the name escapes me for now. It'll come to me. So we need to calculate we want this answer right here. This one right here is 21.1 millimeters of mercury. That's given. We need to calculate that. What's the mole fraction? So we need total moles in the denominator and moles of water in the numerator. So that's the reason I wrote these this way, so that we could find out the moles of each one. 8.55 divided by 342 is 2.5 times 10 to the minus 2 moles. And 17.6 divided by 18 is 0.978 moles. So the total moles are those two plus added together. 1.003. That's total. So the mole fraction then is going to have this in the denominator, and in the numerator, 0.978. So 0.978, 1.978 divided, and that fraction is 0.975 times 21.1, which is 20.6. 20.6 millimeters of mercury. All right. Okay. I'm going to run over. So if you have to go, that's all right. I'll post it today. This evening, I'll post this video. Finish out. This will be part 2. 37. Let's see. When delta G 0 for the reaction is less than 0, the value of K is greater than 1. That's the definition. If you want to prove it to yourself, let's see. I'm looking for the equation here that I gave you guys. I know it's in here. Yeah, minus RT log K. Delta G 0 equals minus RT log K. Right? If delta G is less than 0, that is, it's spontaneous. That means this value has to be positive. And the only way you can get a positive value from that is for K to be greater than 1. If it's less than 1, you're going to get a negative here times a negative gives you a positive. So the K must be greater than 1. All right, 38. Let's see. Madison. Madison had to go. All right, 38. In which case is a process non-spontaneous at any temperature? Here we go back to delta G equals delta H minus T delta S. So if it's non-spontaneous, that means this one has to be positive. So how do you get positive every time? This one would be positive, and this one would be negative. Negative times negative is positive. So there you go. So the answer to that one is D. If delta H is positive and delta S is negative, it's non-spontaneous at any temperature in the forward direction. All right, 39. A flask initially contains 0.1 molar nitrogen. Let's see. 0.1 molar nitrogen gas and 0.24 molar oxygen. 0.24 molar oxygen. Okay. The equilibrium constant for the reaction is 4 times 4.08 times 10 to the minus 4 at this temperature. What's the equilibrium concentration of O2? That O2 should be subscripted. All right, based upon this reaction, N2 gas plus O2 gas is in equilibrium with 2NO gas. Okay. So the K, what is the equilibrium concentration of O2? Well, what's the K value for this one? The flask is initially contains 0.1. Oh, the K is given 4.08 times 4.08 times 10 to the minus 2, is it? No, 4. 4. There we go. And that's equal to, these are all gases, right? So that means we've got NO squared divided by N2 to the first power times O2 to the first power. Okay. So if these are the initial amounts, like 0.1 molar nitrogen and 0.24 molar oxygen, what's the final concentration? So initially we have 0.100 molar and 0.240 molar. And we have 0 here. So the change we know is going that way. So we're going to lose. We want to find out what this is. So let's make X that much and that much. That means we're going to end up with 2X over here. The reason I chose that is so that once we found out X, then we just need to subtract it from 0.24 and we get our answer. All right, so at equilibrium, we had 0.1 minus X and 0.240 minus X, and this is 2X. Okay, so if we put those in our equation, 2X squared over 0.100 minus X times 0.240 minus X. Okay. Notice that this is a very, very small number. That means that this X loss is going to be very small. It's going to move that way, just incrementally small. So we can approximate this expression by 2X squared over 0.1 times 0.24. Okay. And that's equal to 4.08 times 10 to the minus 4. So this is going to be, let's see, 2 squared, 4x squared equals this value times that one times that one. 4.08 there, then times 0.1 and times 0.24. So that's equal to 9.79 times 10 to the minus 6. And X is going to be the square root of this number divided by 4, which is 2.448 times 10 to the minus 6. So x is the square root of that one, which is 1.56 times 10 to the minus 3. Now we just subtract this one from that one. Which is 0.238 molar. Okay. Now, based upon your choices, right? Once you set up the ice table, based upon your choices, you know that X is going to be very small, right? So just look at your choices. Which one comes closest to 0.24 with just a little bit missing? 0.238. Right, so you could save yourself all this on a multiple choice question. You could save yourself a lot of trouble. All right, number 40. All right. Yep, I'm over. So have I got anybody hanging with me? Oh, yeah, I do. Congratulations. Okay, number 40. Determine the reaction order with respect to C for the reaction A plus B plus C equals products. Okay. All right. So A plus B plus C, let's see, yields products. And we want to know the order. Okay. So what would be the rate expression for this reaction? Right. It would be rate equals some constant. That's A, that's B, times C. This would be, let's see, N, M, and P. Okay. So if we're given values here and we want to find out what C is, we want to make sure A and B are constant. So it looks to me like the first two experiments in that list would fit that bill, right? In which case you would ratio the rate of experiment 2 over the rate of experiment 1. And those values would be 6 times 10 to the third. And then the first rate is 3 times 10 to the third. Is equal to K over K, which cancels out. And then you would have a value of A over A to the N. That cancels out. And then you would have B to the M over B to the M because they're equal concentrations, right? We set it up that way. Now this one, C for the second experiment is 0.2 to the P. And the first one is 0.1 to the P. So our expression is 6 divided by 3 is what? 2. That expression right there is 2. This expression is 0.2 to the P divided by 0.1 to the P, which is what? Is 2 to the P power. So P equals 1. Okay? That's why C is the answer. All right, 41. We're getting there. I think I'm going to switch markers. Here we go. Which acid is likely to result in the greatest percent ionization in aqueous solution? The greatest percent ionization. So they're all the same concentration, so it's not concentration dependent. The one that will ionize to the greatest extent is the one that has the largest K value. And that includes C, hydrosulfuric acid, which has a K1 and a K2. The K2 is so small, it doesn't matter. So we focus on K1 and look at the powers of 10, right? Focus there first. We don't have any, they're all different powers of 10. Minus 11, minus 8, minus 4, minus 3. Minus 3 is the largest, 10 to the minus 3 is the largest K. So A, whatever that one happens to be, will have the greatest percent ionization, right? So A is your answer. (42). Methanol, CH3OH, can be prepared by the reaction below. Equilibrium concentrations at 250 degrees C were found to be 0.0960 for carbon monoxide, 0.191 molar for hydrogen, and 0.15 molar for CH3OH. What's the KEQ? Right? This is simple. Right? Take that equation, write out your expression, products to its power, which is 1, and then reactants, CO, to its power, which is 1, and hydrogen to its power, which is 2. Then you plug in the values because we're told what the equilibrium concentrations are. And it doesn't matter the temperature because we're told what the, well, it matters the temperature because this calculation is only good for that temperature. So let's see. Methanol, 0.15. 0. Carbon monoxide at equilibrium is 0.0960. And hydrogen is 0.191 squared. So now we just need to calculate. So 0.15, 0.0960 divided into that, and 0.191 squared divided into that. So I get, let's see, yeah, standard notation. 42, 3 significant figures, 42.8 answers that question. Right. 43. How does this change in stoichiometric coefficient affect the equilibrium constant expression? All right, what did we do from the first one to the second one? It looks like the first one was multiplied by a factor of 2, correct? So what happens to the equilibrium constant when you multiply the whole equation by a factor? The factor becomes the power of the previous equilibrium constant. So Kp for the second one is going to be x squared. Our factor was 2, so it's x squared. 44. A buffer solution consists of 0.1 mole of acetic acid, pKa, 0.1 mole of sodium acetate, in 1 liter of aqueous solution. How much will the pH increase if 0.01 mole of sodium hydroxide is added to the solution? Assume that the volume remains constant. Okay. I'm going to try to use Henderson-Hasselbalch on this one. Plus log of base over acid. So the acid in this case is acetic acid, HC2H3O2, and acetate, C2H3O2 minus, there we go. Okay, what's the initial concentration of all right, we could calculate the buffer pH based upon the concentrations of acetic acid and sodium acetate, but we're going to add sodium hydroxide to it. Right. So what's the concentration of acetic acid to begin with? Right. We start acetic acid, C2H3O2, and acetate, C2H3O2 minus. We start with 0.1 mole of acetic acid in 1 liter. So it's 0.1 molar. And C2H3O2, you know what? Remember when we did the lab with trying to find out the formation constant? We did our calculations with moles of reactants and products, and then we calculated concentration afterwards. I think this one would lend itself to that. So we're starting off with 0.1 mole of acetic acid and 0.1 mole of acetate. Okay. Assume the volume remains constant. That's a key there. We're going to add some sodium hydroxide, but we have to assume that it's still 1 liter. So we can calculate, we can get the concentrations afterwards. Okay, 0.01 mole sodium hydroxide. So we add sodium hydroxide. Sodium is a spectator. The hydroxide is what reacts. So the hydroxide is going to react with this one in the amount of 0.01 mole. 0.01 mole of hydroxide reacts with this one and leaves us with 0.090 mole of that. But when we add this one, we liberate, see, hydroxide reacts with the hydrogen and leaves behind this much. So this is going to add, that minus, this is going to add 0.010 mole of acetate ion, which was freed from that acid. So we have 0.110 mole. Okay, now we can divide by 1 liter. And that leaves us molar concentrations. Now we need pKa, which is 4.74. And this concentration is 0.110 molar. This concentration is 0.090 molar. And we can calculate, all we need is that ratio, take the log of it, add it to 4.74. 0.110 and 0.090 divided. So that is 1.222. This is 1.222. Take the log of it, which is 8.72 times 10 to the minus 2. 8.72 times 10 to the minus 2, and add that to 4.74. Which is 4.83. Oh, I answered the wrong question. how much will the pH increase? Okay, the pH would increase by that much. So 8.72 times 10 to the minus 2, two places to the left, 0.087. Now why? What, I did something wrong. .74. Let's see. We started out with this much. The reaction is 1-to-1, sodium hydroxide, 0.01 mole sodium hydroxide. That plus that liberates 0.01 mole of acetate. So we get 0.09, 0.11. And how much will the pH increase if 0.01 mole of sodium hydroxide is added to the solution? Let's see if I did this calculation correctly. That looks like a stoichiometry problem, right? I thought it was 0.087. The authors think it's 0.04. Let's see, 4.74, correct. 0.1, 0.1, 0.01. Well, they're going to have to convince me that they're right and I'm wrong. Let me calculate it one more time. 0.110 divided by 0.09 is 1.222. All right, then the log of that is 8.7. .087. I don't see how they get 0.04. All right. I think it's this. Authors think it's 0.04. So let's look at the reaction equation. We've got, maybe that's the best way to do it. We've got this one, C2H3O2 plus hydroxyl yields water plus C2H3O2 minus. Correct? All right, we start off with 0.1 mole here. This is 0.010 mole here. That's 0. And this is 0.100 mole here. And the change, this is going to react with that. We're going to subtract that much here. Oops, wrong number. Minus 0.010 minus 0.00. And we're going to add it over here. 0.010. And this is 0.0. So this is going to be 0.110 mole. This is going to be 0. This is going to be 0.090 mole. And it's in 1 liter. Hold on a second. Yeah. It's a total of 1 liter of solution. Now, if it were 1 liter for each, a buffer solution consists of 0.1 mole acetic acid, 0.1 mole sodium acetate in 1 liter of aqueous solution. They're both in 1 liter of aqueous solution. Yeah. If it was each one, If it was 0.1 mole of acetic acid in 1 liter, and then 0.1 mole of sodium acetate in 1 liter, and you add them together, then that would dilute them in half, and that would explain it. But the way it is, we would use this value. This would be molarity. This would be molarity because it's 1 liter total. They go into this expression, and the pH changes by yeah, 0.087. Okay, they're wrong. That's my answer, and I'm sticking to it. It could be that the question was written incorrectly. If the question was not written correctly, then their answer would be right because they're thinking you've got 2 liters total solution. And that would give you half the concentration. All right, so that one needs to be, let's see, I need to edit this before I get too far along. Hold on a second, let me edit this out and change that to no color. Change that to, there we go. And I'm going to save that and then go back to read mode. There we go. Okay. 45. It sounds like I think I lost somebody. No, I didn't lose somebody. How about that? 45. Which chemical equation has KEQ equals to KP? KEQ equals KP. All right. We're looking for that. And if you look in your useful information, we've got an equation that converts from one to the other, which is KP equals KC, or KP equals KQ. Well, actually, it's written this way. Concentration times RT delta N. Delta N is the change in number of moles. So when would this one be equal to this one? When that value is equal to 1. So how would we get this one equal to 1 if that one is equal to 0? Right? Right? Any number to the power 0 is 1. So this change in moles should be 1. Right? Which one of these gives us a change in moles of gas equal to 1? Well, the first one is 2 moles of reactants and 2 moles of products. That would work. Second one is 2 moles of products and 1 mole of, that won't work. Third one is 3 moles to 2 moles. Fourth one is 3 moles to 0. Right? So the change for A is the only one that will give us delta N of 0. So A is the only answer that will satisfy 45. (46). Which change decreases delta G reaction for the following reaction? Okay, delta G reaction is, let me find the equation. Okay, we're looking at partial pressures. All right, so I need to pick the one that includes partial pressures. Okay, RT log P. Delta G equals delta G 0 plus RT partial pressure. And let me see if that's the right one. You know, I think we better use Q. And we can equate Q to the expression that we're given here. N2 gas plus 1/2 O2 gas yields N2O gas. Okay. Which change decreases delta G reaction? We want to make this smaller, right? We want to make that smaller. This needs to be negative. So that means Q has to be less than 1, right? Which would be less than 1. If the KEQ is N2O over N2, and I'm doing that because, well, I should do that because, and then O2 to the 1/2 power. Okay, how do we get this to be less than 1? Well, we don't know the absolute, our starting position. But if we were going to make this less than 1, that means this would have to get smaller and this would have to get bigger. So we would have to shift this way, right? Decrease the partial pressure of N2O. Decrease the partial, would move it that way. That would make this bigger. Make this smaller. So KEQ would be greater. Let me read the question again. What change decreases delta G for the reaction? You know, that doesn't make any sense either. Well, we know the catalyst won't change it. Decrease the partial pressure of N2. Decrease the partial, well, actually B and D both. All right, that's not a good question because it doesn't make any sense. If we want the delta G for the reaction to change, unless I'm using the wrong equation, delta G, no, that's delta G0. Yeah, that's the right equation. This would have to be, in order for this one, in order for delta G to decrease, for this one to decrease, this would have to be a negative number. So that means Q would have to be less than 1. And make Q less than 1, Q less than 1, that means N2O would have to decrease, right? And these would have to increase. So we decrease N2O. Oh, duh. That's what the answer is. Decrease the partial pressure of N2O. Well, okay, that's still not a good question. Because if you decrease this one, you're going to shift it that way. It doesn't say. All right, that's a bad question. 46, I should throw that one out. Let me edit this one and make myself a note here. There we go. Yeah, that question is not written correctly. I better save this if I want to. There we go. Okay, we'll go past that one. Technically, the question is right. It's just not worded very well. Okay, 47. For this galvanic cell, the Nernst equation implies that the galvanic cell will have a more negative voltage if U. Okay, so you need to get the Nernst equation and look at that one, which is 0.05. N, I do believe. And yes, log Q. Okay. So if the Nernst equation implies that the galvanic cell will have a more negative voltage if U, more negative voltage, this one would decrease, become more negative. Right? It doesn't have to be negative, but it would become more negative if we made this one more negative. That means Q would have to be greater than 1. Right? So which would make it greater than 1? If we increased any one of the products, NO3 minus concentration, increase that one? Yeah. If we decreased Br minus, we go the wrong direction. If we increased BrO3, go the wrong direction. Increase the pH, we'd go to the left. Oh, increase the pH. That would increase hydrogen ions, and that would increase, well, that would make it greater than 1, wouldn't it? Increase pH, increase NO3 minus. You know, A and C, that's a bad question too. A and C both work. A more negative voltage if we increase H plus or increase NO3. Yeah, right. 47 could be A or C. Because they're both on the product side, if you increase them, that will increase the value of Q. How about 48? Is this the last one? No. Next to the last one. Okay. A drug is metabolized in a first order reaction with a half-life of 4.12 days. So the half-life equals 4.12 days. And the reaction is first order. So what's the half-life expression for first order? Right? We got it here in your useful information. 0.693 K equals 0.693 over the rate constant. If a patient ingests 1 milligram of this drug, what mass remains after 30 days? Right? We also need, this will tell us what the K is, but first order is log concentration of, let's see, what are we going to call this? Concentration of the drug equals negative K T plus log beginning concentration of the drug. Here we go. So we can find out what the K is here. We just bring the K over here and the days over there. And yeah. So K then is going to be equal to 0.693 divided by 4.12. Okay, is equal to, K is equal to 0.693 divided by 4.12. 0.1682. So now we have our K value minus 0.1682 What's the time? After how long? 30 days. We calculated our K in terms of days, so we're going to use 30 days here. Okay, what's the beginning concentration? Beginning concentration is, well, 100 milligrams. Yes, 100 milligrams. And this is log D after that amount of time. Okay, so the natural log of 100 is 4.6052. 30 times this one. So 30 times. This is minus 5.0461. So we add those two together. And that's equal to minus 0.4409. And that's the natural log of the concentration. So we need E to the minus 0.4409. That's the anti-log because E is the base of that log. So let's see, here's that one. And that's 0.643 milligrams. Closest one is 644. Okay. All right, one more. 49. For the reaction, A yields B, Q is 15, and the KEQ is 5.5. So if we go from A to B, and we're given the Q equals 15, and the K for this reaction is 5.5. 5.5. What statement is true? Delta G and delta G0 are both negative. Okay. We need an equation for minus RT log K. Delta G0 equals minus RT log K. So we got a K here, 5.5 natural log. Under standard conditions, this would be, T would be 25, 273, 298. And this would be 8.3145. 3145 negative. So that's delta G0. So it's 8.3145, 298, change the sign, and then log of 5.5 times. So that's a negative 4 to 4. And for the Q, to give us delta G equals delta G0 minus RT, RT log Q, right? So we know what delta G0 is. We just need RT log Q. So this would be 8.3145. This would be 298K. And this would be log of 5.5. So 5.5, take the natural log, times 298, times 8.3145. And that's delta G equals minus 4,223. Okay, they're both negative. Delta G is positive? Oh, excuse me. That's delta. Then delta G is this is a minus. All right, what am I doing? Oh, it's plus. I'm sorry. That's plus. Plus. Delta G0 is minus 4,224. That gives you a negative. Delta G is, unless I did a calculation incorrectly, 8.3145. Yeah, that's right. 8.3145. This gives us delta G 0. 5.5 natural log 298 times 8.3145. Let's see if I got that one correctly. Yeah, negative RT log K times. Yeah, 424. That's right. And then this one has negative 424 from this part. And then this is 5.5 natural log. And then 298. And then 8.3145 times. And this is 420. Oh, wait a minute, that's 424 also. That can't be. Oh, shh. That's what happens when there's nobody here to correct me. That's 15. Okay, this is 670. 6710. All right, so delta G is positive, delta G0 is negative. So under these Q conditions, the reaction is actually not spontaneous. Delta G0 might be negative, but delta G is positive. All right, that's it. Anybody got questions? Oh, I just remembered the name of that equation we used before with the with that one, like pressure actual, pressure 0. That's Rayleigh law.